First up, we have Jorge Vieyra, who works at ASML. I will let him introduce his talk. Take it away.
Okay. Am I breathing now? Yes. Thank you. Where should I stand for a camera, by the way? I don't know. Somewhere. Thanks for joining. I hope that's not too noisy today, but I hope I'm even noisier. And I'm just going to talk to you about cryptography packages in Julia and what's missing. So let me just start, like, who am I? So, as I said, my name is Jorge Vieyra. I'm a chemical engineer, as in not a cryptography expert. So I'm not that person. And that's the extent of my knowledge. I know from reading that book, the Simon code book, that's where I learned about RSA and symmetric encryption and quantum encryption stuff. It's an old book right now. It's from 2002. So kind of old by most people's standards. And also watch a computer file, a lot of cryptography stuff over there. That's the extent of my knowledge. I'm not I have to emphasize that. I'm not a cryptography expert. I might be a user, but not an expert, okay? And that's precisely the point, because right now, I was quoted once in YouTube, and I posted a comment or something. And then someone like, oh yeah, because this rando is trying to say something. Yes, and I like the term. So apparently I'm just a rando from the internet, just saying things. And that's the way you should think about this talk. It's just one rando person telling you, okay, I want to use these random packages, but I can't. Or there's something I cannot use. So why not? So that's precisely the point. And let me just get started. So what is this talk about? So there was a very nice talk over here earlier today about homomorphic encryption. Super cool stuff. You can encrypt data and do calculations with that. This talk is not about that. Cryptography is usually about number theory and Galois fields and, I don't know, modular arithmetic and elliptic curves and stuff. Some weird math with integers. Also not about that, because I don't know anything about that. Again, I'm not a cryptography expert. But what this talk is about is about the things we use day to day. So all the cryptography packages that we use for communications to protect some of our data, some of the backbone of the things that we use are kind of made out of conventions. It's kind of messy because it's full of acronyms all over the place, full of code names, standards. Is way boring, but needs to be done. Otherwise, it cannot be done. So let me now mention that this is not a rant about, oh, my favorite package in Python is not available in Julia because whatever, or my favorite package in Rust is not available. It's not that either. It's just this is kind of like a template of things that we need to do. This cannot be done by one person. So if someone is interested in these kind of things, this is kind of like a to-do list of things that could be cool. I mean, I know that I'm not selling it very well by saying it's boring. I always say that this is boring, but some people find it quite interesting. I just happen to think that this is okay, but maybe people don't like it very much. So if you find this interesting, oh, this is a to-do list for you. Okay, why this talk? As I always, I don't know if I have emphasized this enough, cryptography in every ecosystem is always a freaking headache. Just keep me family friendly, so freaking. So for instance, in Python, it's kind of documented and people can find their stuff. There's a very nice package out there called PyCryptodome. I like it very much. That's where I learned also a lot of stuff, not only computer file, so I like it a little bit. Let me take this off, because this is... And I screwed the microphone. There you go. Sorry about that. So in Python, we complain about Python stuff, but they made a very nice effort putting all the packages together. There's one package that I like very much, which is called PyCryptodome, which is already the second package, which is PyCrypto. And they talk about all the things, well, they describe all the things that basically a regular rando like myself like to use when we talk about cryptography. I will talk about that in a little bit. Still very messy, because there are things that are not there yet or implemented halfway there, but it's still, you can use it and learn very easily. Rust is not exempt of that either. So there are a lot of packages in Rust. Some of them say, okay, these are super secure because it were implemented in Rust in a super fancy way. And we are very sure that's very secure and whatnot, and very fast. And sure, but it's also very messy. So I have to emphasize, it's very messy. Now, one last thing. So there are a lot of things already done out there. So this is a list that I took from Wikipedia. I also learned things from Wikipedia. And this is just well, I had to cut the list of all the available cryptography packages available. Some of them implement parts of a functionality that people need. For instance, asymmetric encryption or elliptic curves, and some elliptic curves, but not the others. And it's messy. So there's a lot of things out there. So we don't have to reinvent the wheel, but needs to be wrapped somehow. And just pick the one of your choice. I will recommend Button or OpenSSL, but there are a lot of those in case you want. Still very messy. And now, what's available in Julia? OK, let's start with the good things. So random number generators. Why do we need random number generators for encryption or for protecting stuff? Well, first of all, if you want to protect something, you want to make it devoid of any patterns. So that's why you need a random number generator. And as of Julia, I think it was 1.7, now we have a cryptographically grade, secure device that can generate random numbers that you can use. Some people are saying no. OK, good. At least it's there. I don't know if they claim it's cryptographically secure. OK, again, I'm not an expert, but that's what they claim. Documentation has an entry. That's the extent of my knowledge about it. You can use it like that, using the random package. You use the random device, that's the one that's cryptographically secure. And you can generate bytes in that way. So that's a way to use it. I don't know if it's cryptographically secure, but at least you can use it. And the documentation says that's cryptographically secure since 1.7. Is that true? 1.7? No? OK. Next. Cryptographic hashes. So that's to ensure data integrity. So we want to make sure that our data, it's exactly what we think it is. Nobody tampered with it. And that's what they call this thing called hashes. The most used right now is the very unimaginative name called secure hashing algorithm, or SHA. There are several. It's a I forgot the word. It's an acronym. No, but it's a convention. It's not a convention. It's just I forgot the word. Sorry? A standard. Thank you. It's a standard. Thanks. It's a standard that was chosen, and then now we're in the third version of it, and that's what we use. It's documented in Julia. Has an entry. I don't know the extent of that. I don't think it's enough, but OK. It's documented. Has an entry. And that's how we use. OK, good. What's next? Symmetric encryption. OK, that we're getting into something over here. So what is this symmetric encryption? So, well, we want to convert our documents, and we have to make it in such a way that nobody can read them. The easiest and usually fastest way of doing that is just use a fast encryption method, which is called symmetric. So basically, you encrypt in one way using a password or a key. And you can reverse that transformation using the exact same key. That's why it's symmetric. You go both ways using the same key. So that's what I learned in computer file. So OK, good. One of the most used algorithms right now, this I think is considered the most secure at the moment, is AES-2556 or something like that, which stands for Advanced Encryption Standard. Trivia thing, it was not the original name. The original name was Raidnael. I don't know if I pronounce it very bad. Very bad. OK. It's a Belgian algorithm. And so it was made here in Leuven or something. So how do you pronounce it? Reyndal. Kind of. OK. So that's nice. OK, that's implemented in Nettle, which is good. But the thing is that these kind of algorithms work with blocks. And you need to be able to make them secure. You need to make these blocks kind of consistent with each other and encrypted in such a way that cannot be reversed. So there are several modes of operation. I'm not going to go through them. The most advanced one and the one that people like to use is this one called GCM, or Galois counter mode. Don't ask me how it works. Check computer file. But that's not in Nettle. So that's kind of a bummer. It kind of works for keys, but not for messages. So which is, again, a bummer. Technically, it's documented. There's a README entry. That's about it. You can use it like that with Nettle. I use it in some things at my company, but that's about it. So at least it works, and it's fast. So it's, but it's a C library. It's being wrapped. OK, next thing, asymmetric encryption. What's out there? Yeah, well, first, what is it? Usually, as I mentioned, with encryption, with symmetric algorithms, you can encrypt your data, you can protect your data using one key. But the key itself then becomes a problem. How do we transfer this key? How do we protect it? And one way to protect that is using this asymmetric encryption. You generate something that's called a key pair. One is public, one is only for myself, so private. So I can give the public key to anyone that I trust and say, OK, this is my public key. Please, if you want to send me a message, here's my public key. You can encrypt things to me. But the thing you usually encrypt is just the key, and then the message is encrypted with that key, and that's how you transfer stuff. That's the TLDR. Is this available in Julia? No-ish. So in general, no. You cannot access it directly. You can kind of access it via some other packages, the secure layer packages. I'm going to talk about those in a few slides. So usually those are the method, well, the algorithms are used right now, RSA, Rivas, Shamir, and Adelman. So this is the most used right now. It's considered to not be enough anymore unless you use a very large key. The thing that's getting in, like it's a fad now, but I think the thing we should use is this ECC, elliptic curve cryptography. It's not exactly the asymmetric encryption. You need to do some extra things, but it could work like that. And then in order to use those, you need to implement these two methods of exchanging keys using these asymmetric elliptic curves, which one is the ECDEH, the elliptic curve Diffie-Hellman algorithm, not available, or ECIES, the elliptic curve integrated encryption scheme. So in order to actually encrypt something you can send, you need that implementation. And I haven't seen that in Julia. So if somebody can tell me, like, Jorge, you're uninformed, please let me know, because that's my knowledge so far. So more things. I said about sending the message, right? Sending this encryption key, or the public key. Well, how do you send that? How do you encode this information? Different computers have different encodings. ARM is different from Intel. Some are big endian, some are little endian. So that gets complicated. So of course, there's a standard. And then standard is, well, several standards actually. The most widely used is ASN.1, the abstract syntax notation to send binary information, usually certificates, public keys, whatever. Is used over there. That's not, I haven't found anything like that in Julia, except by the use of maybe embed TLS. So that's kind of a bummer. Also, PEM file formats. So there's a privacy mail format, and there's some other formats that I forgot the acronyms of those that get very complicated, like best encryption record and I forgot what the other ones. It's like gets designated encryption record or something like that. So some different formats to send binary information. Again, encoding in such a way that it can be used in several kind of computers. I haven't found anything like that in Julia, and could be used for importing these public keys, for example, or certificates. As I mentioned, OpenSSL or Embed has some support, but doesn't have any clear Julia bindings. You can use them, but it's not very clear how to use them. Also, the documentation is not very good. Well, now I talk about these programs. So sometimes you want to connect to your browser, you want to communications from two computers. So you want to encrypt that communication channel so that you have these standards as well. The secure socket layer, SSL, or the transport layer security. I think the second one is a successor of the first one, but we still use the first one because reasons. You know, technology never really is retired. We just gets older, but keep using it like Fortran, MATLAB. Anyway, so these things are available in Julia. We wrap a few of the libraries. There's OpenSSL and EmbedTLS. I have a personal pet peeve with OpenSSL because I could not really use it directly. I had to use the command line arguments in order to do anything of useful. So I think that the Julia bindings could make use of some TLC, in my opinion. I think they work fine if you use it as intended as a communication layer. But if you use it for anything else, they are not that good. Again, the documentation just points to the OpenSSL library documentation, and that's on the README, and that's about it. So what's needed on this one? Well, more documentation and more extensive wrapping of the functions. I think this is a low-hanging fruit. So if someone gets interested, I think this is very easy-ish. If you want to learn how to bind some encryption libraries, so C libraries. OK, we're getting. You're almost there. We're almost finished. I'm almost end up with my rant-ish. It's not a rant. So we talk about handling keys, sending it over the internet, how to encode them. But if I have them lying around on my computer, someone might be able to copy it, and then that is compromised. So how do we secure these keys? So there are several ways to secure those. So there are some computer chips that are built into your laptop. One is called the Trusted Platform Module. It was the TPM. So that's what was kind of a big deal a few years ago, because then Windows 11 said, OK, you need that as a requirement. You need a TPM. And people were shouting, like, yeah, what if I don't have a TPM? Well, most computers nowadays have a TPM. So that's that thing. It's not a guarantee of success. So some time ago, there was a guy that hacked I think it was some Lenovo laptops using a Raspberry Pi Zero, and just hacked into the wires. But OK, it gets more difficult if it's stored in a chip than if you just copy your hard drive, right? So it's not infallible, but it hardens your security. So that's the TPM. There are similar devices that are external usually. One is called the Hardware Security Module, AHSM. Those are usually attached. Sometimes they're attached to Kubernetes clusters, and that's where they store actually the keys. So another one is the YubiKey. There's an example over there. So YubiKey are like these USB drives that you can just plug into your computer. And yeah, you can also store things there. And the point is that those devices usually encrypt things, and they encrypt stuff by themselves. So sometimes you don't even need the external libraries. Sometimes they just already bind the OpenSSL libraries, like the YubiKey. But it needs to be there. So this one is, as of now, right now, not publicly available in Julia. But this is where I can contribute my small, I can make my small contribution. So I implemented one version of this library for this standard, the public key cryptographic standard number 11. So there are too many of those. So it's sometimes called CryptoKey. That one I implemented. I'm using it right now at my employer. But we're thinking of open sourcing that one. So be tuned on that one. Maybe we have to cut through the red tape to get there. But that's the one I can say, OK, I'm also put my money where my mouth is. So I'm also going to contribute over there a little bit to the community with that. Well, not me, my company. So then I also say that there's another standard which is kind of parallel. This is more used to store these keys remotely. And one is called KMIP, the Key Management Interoperability Protocol. It's similar. It's just a PKCS11. It just works with local hardware. The KMIP works with remote hardware. That's basically the difference. Again, don't crucify me if I'm saying things that are not completely wrong, completely right. I'm not a cryptography expert. So I'm almost there, so don't fall asleep. So now you have the after lunch dip, so but bear with me. So there are a few other stuff that I didn't know where to put. So sometimes people tell me, yes, you have these Jupyter notebooks with Julia that work over CMQ, and it's very nice that you have that. You support Curve MQ, right? Curve CMQ, right? And the answer to that is So what is this Curve MQ? Curve CMQ. Well, maybe the name tells you a little bit. It's elliptic curve encryption implemented over CMQ. So you can just have a protocol between your Jupyter notebook that is encrypted, but not in Julia, because that's not implemented. So we lack that. So that will be something that also we can do. I think that's also low-hanging fruit. And one more thing, that maybe that help a little bit with the binary standards. So sometimes you want to send information over the internet in some nice wrapping. One thing that's called the JSON Web Tokens. Finally, something that's not super complicated. Unless you want me to explain what JSON is. That actually found that's implemented in Julia, and I actually found 2 packages in Julia. That was actually surprised. So I found that like a month ago. I was very, very surprised. Unfortunately, I didn't have time to test them, so I don't know if they're any good. I hope they are, but at least there are 2, and they seem kind of documented. They have README and examples. I don't know if that's enough, but at least they have that. Okay. Long list of a lot of acronyms and weird stuff that I'm just talking about. Like, okay, this is just the summary of that. Maybe my talk would have been summarized with this table. So these are the things that are needed, in my opinion. You can see which ones are available in Julia. Usually just 5 out of, I don't know, I didn't count them, 12. Some of them are OK, but they're not very well documented. And that's the status update as of today. So what can we do about this? Well, if in doubt, just wrap existing library. There are plenty of those. And it's not that difficult. Just ask Christopher how to use libclang. You just get a header, automatically generates all the wrappers and stuff, and then you can just fill in the blanks. It's not that difficult, but it takes some time to work on it. It's a very nice thing if you want to learn how to bind some C libraries, so it's a good learning experience. Most of what is needed is available, just not available in Julia, but it doesn't need to be in Julia. Actually, we don't even need it in Julia. We can just wrap the external libraries and get done with it, or even the Rust libraries. And also, if you do that, don't forget documentation, because otherwise people cannot use it. I usually don't say this, because people that know me think that I'm a Julia fanatic, and they want everything implemented in Julia. But these things, I will say that's the exception. We don't need to implement these in Julia. They don't need to be implemented in Julia. They just need to be wrapped in Julia. That's it, unless you're really, really into it. This being said, of course, a security audit might be in place. Someone needs to qualify that there's no weird things going on, that no memory leaks, there's no things that you're doing such that they can copy all the information out there. Again, not a security expert. You should actually ask an expert if this implementation is correct, but first need to be there, and then we can audit it. So in summary, this is a very small sample of cryptographic functionalities in Julia. I didn't cover not even half of things that are out there. I just covered the things that I think that are needed, at least commercially available. I'm also not talking about fancy homomorphic encryption. I will be happy to be able to use those, not military grade, just commercial stuff. That's it, no more than that. And right now we don't have those things, but I hope this is a template for people that might want to be able to interested in joining the effort. I will be doing a little bit, but again, this is not it's a thing that one person can do, so it needs a team effort. Again, I'm not selling this very well. It's boring, but easy to grab, and it's very satisfying when you have something that works. So I hope we get some more people working on this soon. And that's it. Thank you.
Round of applause. Do we have any questions from the audience?
Oh, questions. Okay, good. Working?
On? Yeah. Is it on? Okay.
Yes.
So you talk about asymmetric encryption, but there is more a story of asymmetric cryptography actually. There are asymmetric cryptographic groups, and there are cryptographic signatures and kind of things. I think it should be separated.
Yes. I absolutely agree. This is a small sample. I agree with you. I'm not even talking about, but the things that are needed, that people just need to use for day to day, are just what I just described over here. I'm not talking even about the fancy stuff.
Yeah, but signatures are kind of separate.
Yes, yes, indeed. I omitted signatures.
Yeah.
Yes, I omitted signing. That's also
I
needed.
actually have a package, crypto signatures, which implement FIPS 1.4 standard, which is compatible with elliptic curves, modular prime groups, and so.
Okay, maybe you should add that to the list as
yeah.
signing. Yes. Okay, good. I will add your package to the list. Yes, thank you.
So what was most of these cryptography libraries end up being like very node dependency C library implementations sometimes. Did you try and wrap any of them with what's it called, the binary builders.jl, and going through the process of creating a JLL for them? Like, was there any recurring pain points?
So I thank you for the question. Yes, indeed. So I only tried to wrap the one that I needed at the time, which is CryptoKey. The other ones I didn't try. I thought, in my mind, oh, OpenSSL is over there. I will try OpenSSL. And it happened like, yeah, I don't know how this thing works. I need to use it right now, and I use it command line. Should be as easy as CryptoKey, I think. Maybe easier, because CryptoKey is kind of weird. It's not really one library. It's one library that's wrapping a set of libraries. OpenSSL should be easier. I haven't tried myself. It should not be that difficult. And with libclang, you can generate the code for you even.
Another thing that I think is missing in Julia is an equivalent of what Python has with SageMath. SageMath is a computer algebra system that implements all the groups, rings, fields, and elliptic curves and so on, and lots of number theoretical algorithms on top of them, determining, for example, the group order of many of these things. And basically, it's a nice framework for combining all the computer algebra world has done efficiently implemented algorithms. It's very widely used by people who want to break cryptography, because if you're looking at a binary and you're trying to reverse engineer someone else's cryptographic implementation, and you find some constants in there and they are Galois fields, they are points on curves, then you need implementation of the underlying algebraic structures. And that's, I think, what should be first addressed in Julia, that you have a cryptographic toolkit like this of the data types, because Julia at the moment is all about ints and floats, but that's not what cryptography uses. They use modular arithmetic, they use Galois fields, they use elliptic curves, and a whole range of other things. And that would be nice to have an equivalent of SageMath.
Thank you for the question. I absolutely love it, but that's exactly the thing that I'm not covering. So I agree that we should have those. That's actually the fun part, actually, you know. So if you are into number theory, you want to study these kind of things, yeah, you should have those kind of libraries. You want to also go into cryptanalysis, well, also that. This is not about that. This is just about the commercially available stuff that is not there. We don't even have the commercially available, not even the state-of-the-art or bleeding edge things. So yes, I agree. We should also have those as well. Maybe you should put it on the list, but maybe it's a separate table. This is like for the bleeding edge kind of things.
Thank you so much. That's it for questions. Let's have another round of applause for Jorge Vieyra. Thank you.